So in this video, we'll look at how to balance a redox chemical equation in an acidic environment. What I'll do here is I'll write the rules out on the left side of the screen, and then I'll kind of scroll up when we're done and go through an example problem. So here we go. So the very first thing we have to do is determine the oxidation states, or the oxidation numbers, depending on how you want to refer to them. So the last couple of videos, we looked at a few different methods to do that. Rule number 2 says you need to separate into half reactions. And a half reaction is essentially you take the oxidation and the reduction reactions and you break them into two separate chemical equations. The third rule basically says you balance each half reaction by doing the following. So each reaction by itself, the oxidation and then the reduction, you balance by using coefficients for everything except O and H. Once you've done that, then you balance O by adding waters. So water contains an oxygen in, so we balance the oxygens using waters. And then we balance H by adding hydrogen ions. All right, so before we scroll on down, maybe we should do a reaction right here. So I'm going to divide the screen into two here. So very first thing to do is write the overall reaction. We often present them what we call a skeleton reaction. So we kind of write things out, and it's not balanced. It just has the reactants and the products, but you know the coefficients are yet to be determined. So this is iron 2 plus permanganate, and it reacts and forms iron 3 and the manganese 2 ion. Okay, now the subscripts are kind of a pain to deal with, so I'm going to leave the subscripts off. And by the way, this is an acidic solution, so I'm going to leave the subscripts off, the little AQs, and just kind of put them back at the end. So first of all, I got to separate into half reactions. So I've got to assign oxidation states, and if you've got a monatomic ion, remember the oxidation state is simply the charge, and otherwise you have to apply the rules. So oxygen is -2 in compounds. We know that manganese must be +7, and the reason for that is that when we add up 4 oxygens and 1 manganese, it adds to -1. We can look at that and we can separate into the half reactions. So first off, if we look at the iron 2 is changing into iron 3. That is an increase in oxidation state. So that means that it is an oxidation. The manganese is going from +7 to +2. That is a decrease in oxidation state. So that is a reduction. So the easy way to remember it, right, is if 7 goes to 2, it's reduced, right? In size, it's reduced in electrochemistry terms as well. And if 2 goes to 3, we're looking at an oxidation number, so the bigger it is, the more oxidized it is. So those are our half reactions, and we're going to balance each one separately. So we're going to start with the oxidation, and we're going to apply the rules, and then we're going to go to the reduction one. And I think for the oxidation, there's really nothing we need to do at this point. So we're going to balance coefficients for everything but O and H. So there's one iron, so that's cool. We're going to balance oxygen by adding water. There's no oxygen. There's no hydrogen. So we're actually at the end of rule 3 there with nothing else to do. However, for the reduction one, this is much more interesting. So for the reduction one, which I'll do in blue just because, we've got a lot more balancing we need to do. So there's permanganate go into manganese 2. We balance coefficients, so there's 1 manganese on each side, so we're actually fine there. Notice there's 4 oxygens, but we don't balance that into rule 2. And we balance the oxygens using waters. If we got 4 oxygens on the left, we need 4 on the right. So we add 4 waters because each water has an oxygen. All right, now we got to balance hydrogens. If we look on the right, we now have got hydrogens from the added water. So we've got 8 of them, and we don't have any hydrogens here, so we need 8 hydrogens on the left. So we're going to have to add 8 hydrogen ions to balance this out. And so that gets us rule 3. So now we need to see rule 4. So let's pause and scroll on up. So rule 4 says balance charge by adding electrons. And the hint is you always add it to the more positive side. So electrons take away charge. So the side that's more positive will need to be adding to. So if we look at our iron, so iron 2 going to iron 3, we can see that the right-hand side is more positive, right? It's 3 positive. So we add an electron to that side to make it 2 positive, and now it's balanced. If we look at the second one, the reduction reaction, it's much more complicated, isn't it? There's 8 hydrogen ions, there's a permanganate, and it goes to a manganese 2 and a water. Well, at least the water doesn't have a charge, but we can see the right-hand side has got a charge of positive 2. The left-hand side has a charge of positive 8 here, negative 1 here, so that's positive 7, and that's positive 2, so that is 5 higher. Okay, so positive 7 is 5 higher than positive 2, so we're going to add 5 electrons to this side. Remember, we always add it to the more positive side because electrons are negative. Okay, and if we go on down through the rules, the fifth rule is we're going to multiply the half reactions and add in order to cancel out electrons. So when we add the reactions together, we're not allowed to get electrons floating around. So notice the top reaction has got 1 electron on the right. The bottom reaction's got 5 electrons on the left. So if we add them up, we'll get 4 remaining electrons on the left-hand side. So the way we're going to handle that is we're going to multiply the top equation by 5, and if you like, the bottom one by 1. And then when we add them up, those 5 electrons on the right will cancel with the 5 electrons on the left. In fact, I normally write my electrons over the arrow, but here we go. So there's 5 iron 2s, okay, plus 8 hydrogens, right? We didn't multiply that one by anything other than 1, so we get to copy our work. And on the right-hand side, we got 5 iron 3s, because we quintupled the top equation. And we got a manganese 2, and we got 4 waters. And again, I think it's helpful to write the number of electrons transferred over the arrow, just because later on we will find we have to use this information. So the last rule then for an acidic condition is check it's balanced. I sure hope so. So it is very easy to mess up, but it's very easy to check if it's balanced because you got 5 irons, you got 8 hydrogens, 4 times 2 is 8 hydrogens. You got a manganese. You got 4 oxygens. Now, in terms of charge, is it balanced? So you got 5 2s are 10. 8 1s are 8. So that's 18 positive. And a negative, so that's 17 positive. Okay. So remember that number. And then 5 3s, that's 15 positive. 1 2, that's 17 positive. 17 plus, 17 plus, so perfectly balanced. So that is totally hunky-dory. And the very last rule is if it is under basic conditions, what we're going to do is we're going to add OH minus ions to neutralize the H plus. And in doing so, it will turn it into water. So let me just go ahead and push this up and finish this off. We were told at the start it was acidic, but maybe we change our mind and it's under basic conditions. What would we have to do? So let's push it up and have a go. All right, so we can see in this equation up here, we've got 8 hydrogens on the left, so we need to get rid of them. And hydrogen ions are not going to persist in basic solutions, so we're going to add the same number of hydroxide ions to get rid of them. Now, of course, it won't be balanced if we add 8 to the left and not to the right. So balancing means adding the same number to each side. All right, what's that going to do? Well, one thing we're going to do is we're going to say, well, 8 H pluses and 8 OH minuses, they're just going to make 8 H2Os. So now we can rewrite this equation, and we can write it as 5 iron 2s and 8 waters. Okay, and a permanganate. Go and form 5 iron 3s, a manganese 2, 4 waters, and 8 hydroxide ions. And actually we can see, there's 4 waters on the right and there's 8 on the left. So we can actually cancel out 4 of those 8. And that gives us our final equation here. So if we wanted to be all fancy and put the state symbols in, we could say 5 iron 2s and 4 water molecules. And a permanganate ion, which is a beautiful purple color, by the way, gives you 5 iron 3s, a manganese 2, and didn't have enough room, did I? And 8 hydroxide ions. So that would be the final balanced equations if it was under basic conditions. And we often worry about acidic and basic because these very highly charged ions are often only stable under very high or very low pH. So they're almost always acidic or basic. If you've had batteries that have leaked and corroded things, you've discovered that in person. So those are the rules. Man, that was really long, wasn't it? So I'll go ahead and give you a few examples to try, and we'll go through them together, and we'll go through a little bit quicker. So it takes a lot of practice doing this. It's a lot of fun. I really enjoy these. I hope you do too. See you in the next video.